Loading of propane. First of all, let me explain to you that propane is one of the byproducts that we make at the Hastings extraction plant. And I'm going to go into some detail as to what devices we use for the measurement of this product as we load it into a tank car and how we convert that measurement into gallons. The propane that we load into the tank cars is loaded by volume. And what I mean by this is the amount of liquid in that tank car is filled to a certain point in that car. Now this is determined by the capacity of that car, and each car has a different capacity. When those cars first come in, we do a DOT inspection of that car, and we log on a sheet the capacity of each car. What we actually measure when we measure in that capacity is the amount of liquid that's left out. This amount of liquid is then converted by temperature to gallons. What we use as a measuring device is what we call a common slip tube gauging device. I have a handout of that I'll hand out here in a very short period of time. And also, as I've already stated, once we load the liquid propane in the car, the temperature is checked, and we use that and take it to a conversion table and adjust it to the amount of gallons that's allowable in that car. This slip tube gauging device that I'm going to hand out here, if you'll take one and pass down through there. Is sometimes commonly called a spitter gauge. The reason it's called a spitter gauge is because it's nothing more than a 1/4-inch valve that when opened, it will let a certain amount of vapor or liquid escape from that car. This escaping vapor or liquid will determine to us what amount of fluid that we have in that car. It has to be determined when we're visually checking that gauge whether it's vapor or liquid. In propane, vapor has no color to it. Once you hit the liquid portion of that car, the liquid part will look white, and that is actually liquid. It doesn't have to be a liquid that you can feel or sight as you would see in a glass of water. Liquid in propane is a white vapor. Let me go over a few of the working parts of this slip tube gauge, and I'm not going to go over the whole parts list here, but the control valve assembly is the top part of that valve. That is, like I've said, a 1/4-inch valve that's no more than an opening device that lets liquid escape. Another important part of that assembly is the pointer cage assembly. This, once you move your outage rod out, will indicate where the liquid is when it's escaping from your valve. Your gauge rod is marked off in 1/4-inch line segments. And what we do when we first set up a car to load, we'll set that gauge rod on a 30-inch setting. And that allows our loaders to go throughout the rack and load several cars at a time. Once they hit on that first setting, they can go and they'll reset that at the final. The final will be determined by each car, the maximum capacity of that car. And during this period of time of the year, most cars are set in the 17 to 18-inch range. What they'll do, they'll set on that gauge rod 18-inch at that pointer cage assembly. They'll leave it set there. They leave that valve open during this whole process. And that again is just a visual way of checking to see, is it still at the liquid stage, the vapor stage, or have we reached the liquid point? Once we reach the liquid point, then we go and we shut the pumps down with switches that's located throughout the rack, and we close the valves on the cars. This method of measuring is probably one of the most effective ways of measuring the product, because you can get an actual reading of where the liquid is, you convert inches to gallons, and you can get a real good idea of the gallons that's been loaded. We've got a couple of different ways of measuring right now. We use a floater type gauge rod assembly, which is nothing more than a magnetic type that floats with the liquid. And we use this slip tube type, which I refer to as a spitter gauge. The spitter gauge will, in the very near future, I feel, be eliminated, because what it is doing during the whole process of loading is letting gases escape. And the environmental people really frown on this. I think at some time in the near future, all our gauging devices will be the floating type gauge. That's about all I have to tell you right now about the way that we gauge liquid propane. Is there any questions?
Very good.
This afternoon I'm going to talk about a topic that many of us may already be familiar with. Some of us may not have any knowledge about it all. And that is a two-stroke or two-cycle engine. When I first come up here, I was going to say, if I mention the word two-stroke, what would you visualize in your mind? And from the variety of people out here, I would think that some of you would think of maybe sitting in front of your fishing boat and your engine being behind you. Some of you may think of being on a motorcycle. Some of you, if I mention two-stroke, may think, well, that might be a pretty good score if I was 2 under par in golf. Well, I'm going to try to bring all of these thoughts together today and centralize those on a two-stroke engine. And the reason I want to talk about two-stroke engine is because they're very widely used in our industry today. To clarify what two-stroke is, just that the piston makes 2 strokes for each 1 revolution of the crankshaft. 1 stroke being down, this we refer to as a power stroke. 1 stroke being back up, this stroke we refer to as a compression stroke. I'm going to go into a little bit of detail of some of the parts of an engine and describe to you, what they do in relation to a sequence and how they perform in that unit. In a two-stroke unit, all these parts would be comparable. You'd have your cylinder, which we refer to as a power cylinder. We'd have our head, our power head. You'd have your piston. You'd have rings. You'd have ports. You'd have intake port and an exhaust port. Also, you have spark plugs. In this illustration, we have dual spark plugs. And we have a fuel valve. This is a means of injecting fuel gas into that power cylinder. The big difference here between a two-stroke engine and a four-stroke engine is these ports. In a four-stroke, you've got valves that let you take a fresh charge of air and fuel mixture into the cylinder, and they exhaust the burnt or unburnt gases. In this two-stroke, we do this with a port system. The rings in this unit right here acts as a seal. They're sealing your compression of air and fuel on your compression stroke, and on your exhaust stroke, they're sealing your exhaust gases from going back down into the unit itself, making them stay in the cylinder until they get to the exhaust part. What I'm going to do now is talk a little bit about what happens during a sequence of one complete revolution of this unit. What you do, and of course my piston's not at top dead center, but if the piston was at the top dead center, and that's where we'll start at on this illustration, you start a downward stroke. You've already, let me back up a little bit. To get a starting point, I need a reference. So I'm going to start 10 degrees prior to top dead center. At that point, we have ignition. The piston is moving up. We have ignition. We've lit off our gas and fuel, or fuel and air mixture. We're starting to create a high pressure. We've got, when the ignition occurred, we've got ignition here, and you're starting to get burning gases on both sides. And this burning gases comes together to get a fully burnt of that mixture. The piston continues on up till it reaches top dead center, TDC as we refer to it a lot. Then that high pressure starts forcing that piston back down in the stroke. As it forces that piston down in the stroke, the farther the piston goes down, the more area you have here. The more area you have, the pressure starts to expand and dissipate a little bit. Once that piston and ring area gets down to this exhaust port, and you'll notice on this illustration that the exhaust port is before the intake port. Once this piston and ring area gets down to there, it starts to let the exhaust gases escape. As it continues on down, and it uncovers those ports completely, all this area here of burnt gases and pressure is escaping. Some point in that sequence, the intake ports will be uncovered, and that will let a fresh charge of air enter the cylinder. The piston will continue down to the bottom of the cylinder, which we refer to as bottom dead center. Both ports are uncovered. You've got your exhaust ports uncovered and your intake ports uncovered. This is letting fresh air come in. It's sweeping out this whole chamber, this whole cylinder area of all burnt gases out the exhaust. This we refer to as scavenging. It's cleaning the cylinder of all burnt gases. As the piston starts back up, let me back up a minute. When we're at bottom dead center, we have completed one stroke or one cycle of that event. Now we're starting to go back up and start into our second stroke. As the piston starts back up, it'll start covering the intake first. And just prior to covering the intake, we're going to inject our fuel gas. This is very critical timing in this sequence. If you inject the fuel gas too soon, you'll waste fuel gas. It's going to escape out the exhaust, and what you'll have is higher fuel cost. But at the same time, if you inject the fuel gas too late in this cycle, you've already closed your intake port, you've already closed your exhaust port, you're starting compression. If you inject that fuel too late in that cycle, then it's going to take a higher fuel pressure to override the pressure that you're developing in that cylinder, and you'll have a lean mixture. This lean mixture will cause misfiring of the unit, which will give you less horsepower. You'll pump less gas. So it's very critical that this fuel gas valve timing is just prior to the covering of this intake port, and once it starts, it gives it your air is going out your exhaust, so it's giving it a free path of flow. It takes less resistance of the fuel gas to enter here. As we continue on up through the cycle, you go into what we refer to as the compression. You've closed both ports are covered. Your rings are sealing. You're starting to compress all your air fuel gas mixture in this cylinder, and you're getting ready to fire it off again. You go on up to approximately 10 degrees before top dead center. You have ignition. You fire off, and we've completed the second stroke of that cycle. That's why, very simply, it was called a two-stroke, because one stroke is down, one stroke is up, 2 strokes for 1 cycle and 1 revolution of the crankshaft. I've got another diagram here to show you, to maybe help explain the pressure in the cylinder. Just as I went through the illustration of the piston coming down for 1, going back up for the second, this is pressure versus time. Cylinder pressure would be on this line going across here. The time would be bottom dead center at the bottom, top dead center at the top. In this illustration, you see ignition just approximately 10 degrees before top dead center. You continue on up with your piston, and then as the piston starts back down, approximately 12 degrees after top dead center, you have your peak pressure in that cylinder. That would be the highest pressure that you'll ever see in that cylinder. As the piston continues on down, you get your expansion or power stroke in the cylinder. Volume increases, pressure decreases to a certain point that it will no longer decrease, but at that point your exhaust ports uncover, your pressure decreases rapidly then. During that area is what we call blowdown. Your intake ports are uncovered. You're starting to get fresh air in there scavenging. You hit bottom dead center. Start back up. You still have that scavenging effect. You go on back up through your cycle. You're covering your intake ports. Your fuel injection valve will open, inject fuel. You cover your intake completely, cover your exhaust. You're going through your compression stroke, where you're compressing that mixture, getting ready for ignition. You got ignition, you're right back to top dead center again. I think it's important that, a lot of us may be familiar with a 2-stroke or 2-cycle engine, but in the gas industry we use both. We use a 2-stroke, 2-cycle, or a 4-stroke, 4-cycle. Probably everyone in here today was familiar with a 4-cycle because if you drove to work today, you drove a vehicle that had a 4-cycle in it. But the 2-stroke is we're unfamiliar with it. We may use it if we use a lawnmower, a weed eater, or a chainsaw, but to understand the difference between the internal working parts of a 2-stroke and a 4-stroke, I thought was important to bring out. I'm hoping after I give this presentation today that everyone would be a little bit more familiar with the working parts of a 2-stroke engine, the events that take place, and that we do use 2-stroke in the gas industry to pump natural gas. Does anyone have any questions?
Why would we use a 2-stroke versus 4-stroke? Cost?
Cost is one reason. Another, and maintenance is a reason. When you're eliminating, your power valves, you're eliminating a lot of maintenance problems. With this, when you go you clean your ports of carbon. With a 4-stroke, you'd have to go in and lap your valves in. There's a lot of maintenance, cost, and time that's saved with this. I'm not an expert on the cost as far as operations or whatever. With a 2-stroke, it would be more efficient because you're doing this. You've got a power stroke and a compression stroke. With a 4-stroke, you've got a power stroke, an exhaust stroke, an intake stroke, and a compression stroke. It takes 4 strokes to do the same amount of work that this 2-stroke's doing with 2. Any other questions?
Very good. That's 12 minutes.
Good afternoon. What I'm going to do today is explain to you what a dehydration plant is, why it's used in the gas industry, and I'm going to walk through a flow diagram. But first, before I start talking about what you don't know, I'm going to let you bring together some of the things that you already know about a dehydration plant. This time of the year, we're very fortunate because I've got some very good examples to bring forth and let you see what you already know about a dehydration plant. This week, one morning we had frost on our windshield. This frost was a collection of dew during the night which had frozen. We had to scrape it off the windshield. It was a problem. It was something that we had to deal with before we could go ahead about getting in our vehicle and coming to work. This morning, as I went out to get in my vehicle, there was dew on the windshield. All I had to do was turn on the windshield wiper, the dew was wiped off the windshield, and it was less of a problem. This dew was nothing more than moisture that had condensed during the night due to a temperature change. In our houses, we've got a very small dehydration plant. We've got an example sitting right back here on the floor, a dehumidifier. What it does, it takes the moisture out of the air, condenses it to water, and we dispose of the water. Very small, yet exactly what a dehydration plant does. Why do we have to take the water out of the gas? It does, as we've heard earlier in some of these presentations, it plugs the pipeline. As long as it's in water form, we can run a pig or a ball through the line and we can shove that water out. No problem. What happens during this time of the year when the temperatures get a little colder, we're dealing with pressure then and temperature, and that water turns into hydrates. Hydrates being snow-like or ice-like formations in the pipeline. I want to show you here that gas plus water equals hydrates. Hydrates is what causes our problems in the gas industry. Once they get into the pipeline, they'll form solid formations and create blockages. These tend to collect at bends in the pipeline, at valves, and at meter runs. The reason they're collecting at these areas is because that area in the pipe, the flow of the gas changes speeds. The velocity of the gas is changing speeds, causing a formation at that area. What I want to tell you is how a dehydration plant actually works, how it contacts the gas, and how it absorbs the water and then removes the water from that. What I've got with me today is a diagram of a typical dehydration plant. I'm going to go over mostly just the major components of this dehydration plant, and the two major parts of this system is the reboiler and the contactor. The contactor is also known to some people as an absorber. It's where the fluid that we're using absorbs the water from the gas, and then we circulate it back to the reboiler and evaporate that liquid off. What I've done in this illustration is used green and orange as showing you the different colors of the flow of the liquid. The liquid that we use in this dehydration unit is triethylene glycol. Triethylene glycol is used because we can go to such a high temperature to evaporate the water. 404 degrees Fahrenheit is where triethylene glycol starts to decompose. Therefore, on our reboiler, we try to maintain a temperature between 380 degrees and 400 degrees. Now I'm going to walk through the flow path here of the glycol as it goes through the system to the contactor and explain to you a little bit about what happens in the contactor. As the glycol is heated to 380 degrees in this reboiler, the hotter glycol will actually come to the top and spill over into the surge part of the reboiler. It goes through a system of heat exchangers, which is exchanging heat of our dry glycol, which is the orange glycol leaving, and the wet glycol coming back to the reboiler. As it goes through those exchangers, it gets to the pump. The pump is what's necessary to build that glycol pressure to a point just above the gas pressure that's in the contactor. We build that pressure, go through a series of gas to glycol exchangers here, and it gets to the contactor. In the contactor, the glycol enters at the top. Gas flow enters at the bottom, and you've got two mist pads here. The top mist pad will eliminate any glycol from being carried out of the contactor. The bottom mist pad is just, in this example, is acting as a scrubber. Any liquids that the gas is bringing into the contactor will collect here, drop out, go to a drain. As this glycol comes in this contactor, it works its way down the contactor. As it's coming down, gas flow is going up through a set of trays, bubble trays. And I've got an illustration that I hope to clarify that up a little better. The gas flows up, glycol flows down. Glycol is absorbing the water, collecting it down here till it gets a level. We have a level control in this, and once it reaches that level, to maintain a constant flow of this, it'll dump. This illustration, it's dumping it back to the pump, going back to the reboiler. A lot of the systems that we have today, we dump directly from the contactor back to the reboiler. We're using pressure alone to move the glycol. Once that wet glycol goes back through the pump, through a control valve here that takes it through a set of coils in your reflux column, it goes back through a heat exchanger, through a skimmer system, a couple of filters, back to the reflux column, and inside this reflux column we have what we call burl saddles or ceramic saddles. They're nothing more than just pieces of ceramic in there that's laid in there or poured in there, and it causes that glycol to drain down. As it's draining down the wet glycol, you've got moisture and heat that's being created here in your reboiler, the water being evaporated, trying to work its way up. That's what this coil here is for. Everyone in here knows that water will evaporate. The boiling temperature of water is 212 degrees. So water is going to evaporate at 212 degrees or above. Well, we've got 400 degrees here. Anything, if we get too high, we're going to create a loss of glycol, and it's going to go out to a vapor outlet. So what we want to do, we want to just keep this temperature just a little bit above 212 degrees. What we aim for is about a 215 degree temperature right here. That's what that coil is for. It's a heat exchanger. It's cooling this rising heat to somewhere around 215 degrees, condensing glycol, letting it fall back. We're saving glycol. We're not wasting glycol. But at the same time, it's keeping the temperature high enough, the water will go ahead and vapor out. I talked real briefly about the exchangers here. There's a real important in the flow of this glycol because you're heating it to 400 degrees. Most pumps can't stand that kind of temperature. If that glycol hits that pump at 400 degrees, it's going to burn up packing and it's going to burn up the rings or whatever's in that pump. These heat exchangers starts bringing that temperature down of your dry glycol to somewhere around 200 degrees. We're looking for a temperature right around 200 degrees before the pump. And we've got another set of heat exchangers there, or in a lot of cases in some of the older systems, you just got distance. You're wanting that glycol that enters the contactor to be somewhere close to the gas temperature. Ideally, the gas temperature at a contactor should be somewhere between 80 and 100 degrees. As I'd said a little bit earlier, I've got a diagram here to explain a little bit more about the working parts of a contactor, and I think it's important to let you see how exactly the gas and the glycol has made contact in there and how we're absorbing the water. This is not one of the best diagrams, but we'll see how it shows up overhead.
John, quick question. Who designed that system, that dehydration system? Is that a company?
CE NATCO, the one I'm talking about, yes. This is the contactor, absorber. In here we have a series of trays, as I've talked about. Here's your wire mesh extractor, one at the top. Each tray has what we call bubble caps in it. As the gas flows up, the glycol wants to come down. The gas is forced, you'll see tiny holes here through these trays. The gas flow has to go up through those holes. As it's going up through the holes, it goes up through a bubble cap. Gas flows up, it goes up, comes down through. You've got a weir on here that holds this level of glycol. Gas is forced through the glycol. It has to go through the glycol. As it goes through, the glycol absorbs the water. As that glycol absorbs it, it comes through that tray and there's a downcomer there. You'll see them at each level. As it's absorbing the water, it spills over to the next level. The same thing happens again. You've got the same gas going through the bubble tray, forcing it through the glycol picking up water, picking up a level, going to the next tray. As it continues to come down through the system of trays and bubble trays, it's collecting the water, and the farther it comes down, the more water is collected, till it gets down to the point of your outlet. And then it's dumped back to your reboiler system. What I've tried to, by going through this illustration of the dehydration plant, I've tried to let you know that it is a necessity to take the liquid, the water liquid, out of the natural gas. If we don't, it creates operational problems for us during the winter. I've tried to bring in some illustrations of things that we all are aware of. Dew in the grass, or dew on our windshield. What happens to the dew as the temperatures change? It turns to ice. The very same things occur inside our pipeline. We create the problem by compressing gas. All gases, whether it be the air that we breathe or the natural gas that we pump, they have the ability to hold water. Through compression, we're actually heating that gas up. As it's heated and compressed, that ability to hold water is lessened. The water will drop out. So prior to a dehydration plant, we have a separator in the system that will collect free water. I hope the information that I've shared with you this afternoon will give you an idea of what a dehydration plant is, how it's used, and why we must use it. And also, I hope that we understand that a lot of these terms and things in the gas industry are actually just natural occurrences that they happen every day in our lives. We just need to relate these to terms used in the gas industry. Is there any questions or that I can answer at this time?
Good job.
Got my tongue tied right there.